We are on a collision course with the massive neighboring galaxy, Andromeda, a system comprising several hundred billion stars. This collision will lead to a shared plunge, drastically transforming both galaxies. The Andromeda Galaxy has been pivotal in shaping our understanding of the universe, demonstrating that it does not revolve around Earth. As one of the most studied galaxies for over a century, Andromeda has been instrumental in advancing astronomy. Its importance was first noted when it revealed that the Milky Way was not the sole galaxy, fundamentally altering our comprehension of the cosmos. Centuries of progress, from early observations to cutting-edge advancements like the James Webb Space Telescope, have unveiled astonishing new details about Andromeda. A mere 400 years ago, the Milky Way appeared as a faint band of light in the night sky, a view limited by the primitive technology of the time. Galileo Galilei, in the early 17th century, used his telescope to reveal that this band of light was an enormous collection of stars, planets, and celestial objects. His observations debunked the belief that the Milky Way was the center of the universe, instead showing it to be a sprawling star system. In 1750, British astronomer Thomas Wright hypothesized that the Milky Way was a flattened layer of stars containing our solar system. This theory, however, was constrained by the technological limitations of the era. By the 1920s, major strides were made in astronomy. Edwin Hubble, using the 100-inch Hooker telescope at Mount Wilson Observatory, demonstrated that distant nebulae, including Andromeda, were distinct galaxies containing billions of stars. This discovery fundamentally reshaped our understanding of the universe. The Andromeda Galaxy, also known as M31, has been observed since at least the 10th century when Persian astronomer Abd al-Rahman al-Sufi described it as a small cloud. Al-Sufi's sharp vision allowed him to identify Andromeda without telescopes, an impressive feat made possible because it is one of the few galaxies visible from Earth without special instruments. In 1612, Simon Marius provided one of the first telescopic descriptions of Andromeda, laying the groundwork for future astronomers. Charles Messier catalogued it as M31 in 1764, making it easier to study. In 1864, British astronomer William Huggins analyzed Andromeda's spectrum and found it to be different from typical gaseous nebulae, a groundbreaking observation. Andromeda, with an estimated mass of 1 to 2 trillion times that of our Sun and a history spanning approximately 10 billion years, has undergone significant evolution through the merging of smaller protogalaxies. Earlier, astronomers believed Andromeda was significantly more massive than the Milky Way, but recent research suggests their masses are closer than previously thought. Physically, Andromeda is larger than the Milky Way, spanning about 220,000 light-years in diameter compared to the Milky Way's 100,000 to 175,000 light-years. One fascinating feature of Andromeda is its active galactic core, powered by a supermassive black hole with a mass of 110 to 230 million times that of the Sun. Observations from advanced telescopes like the Hubble Space Telescope have revealed 2 points of brightness near its core, suggesting intense gravitational interactions and the presence of this massive black hole. Andromeda is rich in globular clusters, estimated at around 460, each containing hundreds of thousands to millions of stars. This abundance indicates a history of galactic cannibalism, where smaller galaxies were absorbed into Andromeda, enriching its stellar population. Recent observations suggest Andromeda may transition from a spiral galaxy to a ring galaxy, a rare type characterized by circular ring-like structures of bright young stars. Such formations can arise from galactic collisions or when a smaller galaxy passes through the center of a larger one. The impending collision between the Milky Way and Andromeda is a cosmic event predicted to begin in about 4 billion years, lasting approximately 2 billion years. This grand encounter will culminate in the formation of a new supergalaxy, informally dubbed Milkomeda by astronomers and enthusiasts. The merging process will involve dramatic gravitational interactions and tidal forces, profoundly impacting both galaxies. As they approach each other, their immense gravitational forces will distort their shapes, creating elongated tidal tails and triggering a series of complex gravitational interactions. The overlap and merging of the two galaxies will not be smooth. Instead, it will be marked by turbulent and dynamic changes as their structures are dismantled and reshaped. One of the most dramatic outcomes will be the formation of new star clusters. As the galaxies collide, their gas clouds will compress, leading to bursts of star formation. These stellar nurseries will produce intense gravitational forces, causing the gas to collapse and form new stars, often grouped into clusters that will enrich the new supergalaxy with fresh stellar populations. At the same time, gravitational turmoil will alter the orbits of existing stars. Stars that once had stable orbits around the centers of the Milky Way or Andromeda will be flung into new, more eccentric paths or potentially ejected into intergalactic space, becoming rogue stars no longer bound to any galaxy. This redistribution of stellar material will contribute to the formation of new cosmic structures, creating intricate networks of star streams and clusters that blend the remnants of both galaxies. In addition to forming new stars and clusters, the merging process will create vast, complex structures within the new galaxy. The gas, dust, and stellar debris from both galaxies will settle into new formations, creating expansive regions of star formation, warped arms, and potentially unique galactic features that are a hybrid of the Milky Way and Andromeda's original forms. Over time, these structures will evolve, influenced by the dynamics of the combined galaxy. The supermassive black holes at the centers of the Milky Way and Andromeda will also play a crucial role in the merger. As the galaxies coalesce, their central black holes will eventually merge, forming an even larger supermassive black hole at the heart of Milkomeda. This merged black hole will emit powerful energy and significantly impact the surrounding stellar environment, contributing to the new galaxy's active and evolving structure. Ultimately, the merger of the Milky Way and Andromeda will result in a completely transformed cosmic landscape. Milkomeda, the new supergalaxy, will be a massive entity composed of the blended material from its predecessor galaxies. It will feature a rich tapestry of new star clusters, altered stellar orbits, and restructured galactic dynamics. This process of cosmic evolution, driven by collision and merger, will shape the future of the local group of galaxies and offer an intriguing glimpse into the long-term dynamics of galactic interactions. The merger will dramatically alter our night sky and potentially impact Earth's environment, though this transformation will occur long after humanity is gone. In approximately 5 billion years, our Sun will expand into a red giant, rendering the solar system uninhabitable. The merging of Andromeda and the Milky Way raises questions about the fate of our solar system and the formation of new galactic structures. The resulting cosmic interactions may create habitable zones for potential life. The inevitable approach of the Milky Way and Andromeda galaxies towards each other in the vast expanse of space marks the onset of a remarkable cosmic merger. As this monumental event unfolds, astronomers anticipate significant transformations in their structures and dynamics. Currently, the Milky Way and Andromeda are spiral galaxies, distinguished by their iconic arms extending outward from a dense central core. These spirals are shaped by the rotation of stars and gas around a central nucleus, creating patterns visible from Earth. However, as the galaxies draw closer, gravitational forces will distort their shapes, stretching and pulling their spiral arms into elongated tidal features. These spectacular structures, composed of stars, gas, and dust, will form an intricate display across the cosmic canvas. The collision will also ignite intense bursts of star formation within the emerging supergalaxy. As gas clouds from both galaxies collide and compress, they will heat up, triggering the birth of massive luminous star clusters. These clusters will become nurseries for young stars, whose energetic radiation will illuminate the surrounding cosmic dust and gas, creating dazzling celestial phenomena. Beyond altering their appearance, the merger will have profound effects on the internal dynamics of the galaxies. Gravitational interactions will cause a reshuffling of the orbits and velocities of stars and gas clouds. Some stars will be hurled into erratic trajectories, while others may be ejected entirely, becoming rogue stars drifting through intergalactic space. At the centers of both galaxies lie supermassive black holes, each millions of times more massive than the Sun. As the galaxies merge, these black holes will spiral toward one another, emitting gravitational waves as they draw closer. The final stages of their collision will release immense energy in the form of gravitational waves and radiation, ultimately creating an even more massive black hole at the heart of the new galaxy. This powerful central engine will influence star formation and the behavior of gas and dust within the galactic core, potentially triggering quasar-like phenomena as material accretes onto the black hole and emits intense radiation. On a larger scale, the merger will contribute to the evolution of cosmic structures in the universe. Galaxy mergers and interactions play a crucial role in the hierarchical formation model, where smaller structures combine to form larger, more complex systems over cosmic time. Observing the Milky Way-Andromeda collision offers astronomers a unique opportunity to study the mechanisms driving galaxy formation and evolution, providing insights into the intricate processes at work during such events. The merger will also affect the distribution of dark matter within the resulting supergalaxy. This enigmatic and invisible form of matter, which constitutes a significant portion of the universe's mass, plays a key role in shaping galactic structures and gravitational interactions. The merging dark matter halos surrounding the Milky Way and Andromeda will influence the overall distribution of dark matter in the new galaxy. Studying these effects will provide critical clues about the nature and properties of dark matter, helping to unravel one of cosmology's greatest mysteries. The collision will also incorporate the satellite galaxies orbiting the Milky Way and Andromeda into the merger. These smaller galaxies may either merge with a supergalaxy or be torn apart and assimilated into its extended halo of stars and gas. The fate of these satellites will depend on their orbits and velocities relative to the merging system. Some may survive relatively intact, becoming dwarf galaxies within the new supergalaxy, while others may be disrupted and absorbed. For our solar system, the merger poses no direct threat. However, gravitational disturbances and an influx of cosmic rays could have subtle effects on Earth's environment and cosmic ray exposure over geological timescales. Additionally, the night sky will transform dramatically. The positions and distributions of stars, star clusters, and nebulae will change, potentially creating new constellations and celestial landmarks that could shape the cultural and navigational aspects of any future civilizations. In conclusion, the collision and merger of the Milky Way and Andromeda galaxies represent a cosmic spectacle of unparalleled scale. This process will reshape both galaxies, creating a new supergalaxy that blends the material and characteristics of its predecessors into a unified cosmic entity. From the reformation of spiral arms and the birth of new star clusters to the coalescence of supermassive black holes and the redistribution of dark matter, every aspect of this merger will leave a lasting imprint on the future evolution of the local group of galaxies. Studying this event allows astronomers to witness the transformative power of gravitational interactions in shaping the universe, reminding us of the dynamic and ever-changing nature of cosmic evolution. Galaxies collide, merge, and give rise to new structures and phenomena, fueling awe and curiosity in the exploration of the cosmos.